All right, I want to show you a couple of maps that looked good to me. Unfortunately, there were some maps that didn't look good. And I think probably the issue was that some people were trying just to use what EPANet gives you and turned that into their maps. And EPANet is good for analysis, but it's bad for visualization. So what I needed in phase 2 was 2 annotated maps. And let me show you one of those annotated maps that looked pretty good. It's a student submission. Let me zoom in a little bit so that you can see that. So here's this student's network. And so you'll notice that each one of the pipes has a flow rate that's going through it that's annotated. It's got the diameter of the pipe. It's got the length of the pipe. Got the pressure at each junction. Now there's a couple of issues that I'm going to have to mention to this student. Like for example, they used a non-standard diameter. 521 millimeters isn't one of the available diameters. That's not on the list. You can't buy that diameter, and you can't buy a 520 millimeter diameter. So they're going to have to make some adjustments to their analysis, but the dimensioning looked good. The only thing that I guess I would add to this is it looks like they didn't put the flow rate at the junction. They've got the flow rate through the pipe, but not the flow rate out through the junction. So this is one that, I mean, just like in terms of how the space was used, it was very effective. Like you can see the annotation clearly, and the size of the text is good, the size of the labels is good, and so on. So that was one that looked really good. Here's another one that looked excellent, I thought. This is, let me show you first of all the network at, and the 2 maps that you're supposed to do, of course, are the network at the static condition and also the network at the design flow. So this annotation is just another student's effort to kind of show what's the pressure in the network. So the pressure at each junction, the elevation at each junction, and the flow rate out. So that's what I need to know about a junction. Is how much water's coming out there, what's its elevation, and what's the pressure. So this looks great. And then for each pipe, what's annotated is the diameter, the length, and the flow rate. So I don't have any complaints about this one. I think it's great. And so this is showing, it looks like this is when we have the maximum flow rate going through this pipeline. And the criteria here that I'm looking to see in the map, is there any place where the pressure is below 240? Because that's our lower limit. And you're going to experience the lower limit when you've got the maximum design condition. So, for instance, see this pipe IH? It might be, you could probably make that a little smaller. Isn't the minimum pipe size diameter 100 millimeters? So I think this student could optimize a little bit further, because see how pipe H has a pressure of 726 kilopascals? That pressure is much higher than it needs to be. So you could make pipe HI a little bit smaller. Likewise with pipe AM, it might be possible to downsize that pipe a little bit more, because the pressure here at the end of it at location M, 635, you're nowhere near that lower limit. So you might as well make it smaller to save your client some money. So I just wanted to show you a couple of maps that look good, and you can do your maps by hand. You can do it, I don't know if this was PowerPoint or some other tool. It looks great, whatever it was. I don't want to put anybody on the spot, but Courtney's the one who made this nice looking map. Courtney, what tool did you use to generate this map?
I just actually did like the snipping tool and then went into Word and added the text from there.
Okay. So
and I use EPANet.
The line locations and maybe the labels of the junctions was built into EPANet?
No. Well, just the junctions themselves, like everything that's labeled except maybe the R at the top,
Okay.
was the only thing that was actually there. Everything else I just added text boxes in
Oh,
around the junctions.
okay. Yeah, that's really clever. So you just took the lines from EPINet, snipped that, and then did you do it into Word, did you say?
Um,
PowerPoint might
no,
be
actually,
easier.
I'm sorry, I used PowerPoint for that.
PowerPoint I
That's what I
find
did.
is pretty good because it makes it easier to like rotate the text. I noticed that you have like your labels at an angle, and PowerPoint does a good job for that.
Yeah,
So
that's
good
what I
job.
used.
Sorry to bust
Thank
your
you.
anonymity, but now everybody knows you did a nice job on phase 2 of the project. All right. So if you have questions about the project, I'm going to be trying to get my feedback to you as quickly as possible. You know, I focused on the exams over the weekend, but I want to get you as much feedback as early as possible. We still got a little bit of time, a week until your final report is due. Let's talk about hydraulic jumps, continuing on with some of the topics we first touched on last week in Chapter 13. We looked at the Bellinger momentum equation, but we didn't yet try it out. So that's what we're going to do now. Here's the Bellinger momentum equation. It allows us to predict what is the downstream depth with a known upstream depth before the hydraulic jump occurs. Here's the flow rate through a 9.4 meter wide rectangular channel. We want to know two things. First of all, what's going to be the new downstream depth? So solve for y2. And you'll notice that the version of the equation that I've included is the one that uses the Froude number. What I showed you in class last time was the Bellinger momentum equation can either be written in terms of the Froude number or as a ratio of the critical depth to the upstream depth. Let's try this one with the Froude number. All right, so solve for y2, and then here the delta E is going to tell us how much energy is lost in the hydraulic jump. And remember that that's a feature, not a bug. Losing energy in a hydraulic jump is something that oftentimes is very desirable, and it's used in stilling basins to ensure that the water doesn't have too much energy that's causing damage and scour downstream. So we want to know the delta E that occurs in this hydraulic jump. So let me pause for a moment, put you in the breakout rooms, and solve for y2 delta E. And delta E is going to give you the change in energy. So here where it's asking for the fraction of the initial energy that's lost, what that's really saying is what was E1 originally, and then how much of the energy that there was at 1 is lost. So you need to solve for delta E, but then also express that as a fraction of the initial energy that was there. Okay, to the breakout rooms. All right, so we're going to take a look at the solution now. I've already been through each of the breakout rooms, and it seemed like everybody had made pretty good progress there. All right, so first things first, we need to calculate the Froude number to find out, presumably it's supercritical. You know, if it wasn't supercritical, then you're not going to see a hydraulic jump. Every hydraulic jump starts out as supercritical flow. So the Froude number formula that I used is the simplified version. Since it's rectangular, I get a Froude number of 5.238 and put that into, well, I also did it the full way just to verify that regardless of whether you had a, if you had a trapezoidal channel, then you couldn't use the formula for this. You couldn't use this formula because it relies on a flow per unit width. And if you have a non-rectangular channel, then lowercase q, flow per unit width, doesn't quite have the same meaning. Unless it's very wide. Unless it's 20 times wider than it is deep. So anyhow, with the Froude number, you can see the substitutions that we make. In order to calculate the downstream depth after it jumps is going to be 5.956 meters. So it started off at a depth of 0.86, and it jumps up to nearly 6 meters in depth. So that's a pretty dramatic hydraulic jump. In terms of energy loss, the delta E, you can see, is 6.46 meters. So that is the magnitude of energy that's lost through the jump. But to help us understand whether that's a little or a lot, it may be useful to express that as a fraction of the initial specific energy. Like what percent of the energy was dissipated with this hydraulic jump? Because we don't necessarily know how much specific energy was there to begin with. And so here's how much energy there was to begin with. We add together the depth and the velocity head upstream before the jump. So there was 12.66 meters of energy at the beginning, and we lost 6.46 meters. So as a fraction, that means that we've lost about 51% of the specific energy that was in the water before the jump as it went through the transition. And that's great. You know, like I mentioned before, it can be very useful to dissipate that energy. So that's our first chance to use the Bellinger momentum equation. It won't be your last. You've got, I think, homework problems where you'll go through this similar process. For those, you may need to apply these ideas with a non-rectangular channel. So if you had a trapezoidal channel, I wanted to review a little bit of information about how you could find the depth to the centroid, h bar. So if you had a channel with a bottom width of 3 meters and the flow depth is 1 meter, like this, and we've got 1-to-1 side slopes that's been indicated there, then this formula allows us to calculate the distance from the bottom up to the centroid. And so then delta H, which is from the surface of the water down to the centroid, would be simply y minus this distance. So this is the most useful formula I could find somewhere that gives us the distance from the bottom up to the centroid. So let me just, for these numbers, show you that the way that you could apply this formula to find the depth of the centroid if you have a trapezoidal channel. So you can see that the distance from the bottom up to the centroid for a channel that has a top width of 5 meters and a depth of 1. And so that's maybe something that I need to emphasize here, that the top width is capital B and the bottom width is lowercase b. So if this has a bottom width of 3 meters and a depth of 1 and side slopes that are 1-to-1, then that means across the top it is it's 5 meters. Across the bottom it's 3, so b, which goes into this formula, is 5, and lowercase b is 3. So now back to this one. Distance up to the centroid from the bottom is 0.54, and think about, does that make sense for a trapezoid? The centroid is the center of area, and so if the depth is 1, the center of area is going to be higher up than the middle. The middle is 0.5. So the depth of the centroid, if it's rectangular, is just half the depth. But this is wider at the top than it is at the bottom. So it makes sense just from kind of an instinctive level that the center of area is going to be above the midpoint, because this extra width across the top drags that a little bit higher. So it's always good when you do a formula to just make sure that it kind of matches up with what reason and your instinctive expectations would be. So from the bottom up to the top, 0.54, which means h bar, which is the depth from the surface down to the centroid, would be 1 minus that distance, so 0.4583 meters. All right, so hopefully that will be useful if you ever do face a trapezoidal channel that has a hydraulic jump occurring. All right, now we're going to talk about the location of hydraulic jumps. And we're going to talk through the concepts that relate into where the hydraulic jump occurs And then also I'll show you some formulas that are used to estimate the length of the hydraulic jump. So this is the most simple case. The most simple case is that we have an underflow gate. So this shaded piece here, you could think of it just as like a metal gate that goes across the width of a channel, and the water can't flow at its usual depth because of this gate is in the way. And so the water level rises behind the gate, and so it's got enough energy now, the water has pooled upstream of the gate, that it's flowing under the gate relatively fast because, you know, it's a lot of pressure when the water pools up to this depth. And so the high pressure is pushing the water under the gate at a high velocity, and we have this given depth, y1. And one of the interesting things I'll point out is that the water continues to contract. So its minimum depth point is a little bit lower than how much the gate is opened. And that's because the water is continuing to accelerate. Because of the pressure behind the gate, it doesn't stop accelerating instantaneously. It stops accelerating, it reaches some minimum point, and then that's when the hydraulic jump occurs. Now this may be relatively unusual for the hydraulic jump to occur so soon after a gate, and the reason why is that the downstream depth plays a role in determining when the hydraulic jump occurs. So a hydraulic jump has to jump up to a different depth. It's looking for its conjugate depth downstream. And so a hydraulic jump is only going to occur when the new depth downstream can be supported. And so Manning's equation is what would tell you what's going to be the depth of flow in the channel downstream, like how rough is that channel, what's the geometry, what's our flow rate. So Manning's equation would tell you y2, the downstream depth, and what the hydraulic jump is going to do is it's going to jump through that transition when the downstream jump that it's looking for exists. So point out this thing, y prime 1 means the depth after the hydraulic jump, and y2 means the normal depth. And so I've defined those terms here to the left of the drawing. Now, a rating curve is explained in your book as the relationship between flow rate and depth. And so we have a jump rating curve and a tailwater rating curve, and they're both on top of each other in this ideal case. We've only got 9 minutes left, but even if we had 20 minutes left, I don't think I could adequately explain a rating curve. It's the sort of thing that you need to look at and think about and just kind of reflect on for several minutes, because it's not immediately obvious what it is and how it works. But let me just take a quick stab. But I just say all that to really drive home the point that this is one of those times when I really hope you spend a little extra time in the book thinking about the concepts and looking at this figure and making sure it makes sense to you. So on the vertical axis is depth, and on the horizontal axis is flow rate. So what we're saying is there's a curve that says what is going to be the depth and the flow rate, both for the channel downstream, and that's the tailwater. So the tailwater is downstream of some hydraulic apparatus like an underflow gate. So the tailwater rating curve is defined by Manning's equation. The jump rating curve is defined by like how sharp is that plate, the Bellinger momentum equation, what's going on upstream of it. So the ideal case, we would only see this immediate jump when the jump curve and the tailwater rating curve are on top of each other. Let's look at most of the time how things may be different. It could be the case that the jump moves downstream a bit. So now look at this sketch. We have a hydraulic jump again. The gate is closed a little bit more. So see that this gate is open a certain amount. In this next case, the gate is closed a bit further. So if you close the gate more, the headwater, the water upstream of the gate is deeper than it was in this first example. Look that it's risen a little bit more. So the water's moving faster, and it's going to have to gradually increase its depth until it gets to the point where the conjugate depth is equal to the normal depth downstream. So this dashed line represents where the water would want to jump up to if it could jump immediately. Just based on what's the water level here, if you have a really shallow upstream depth in the hydraulic jump, then the downstream depth is going to be really deep. Remember that our formula says that when you have a high Froude number, there's a bigger extreme between the upstream and the downstream depth. So the dashed line is kind of where the hydraulic jump would like to be if it jumped immediately. But since the normal depth of the channel is just this Y2, the hydraulic jump can't go all the way up here because that's not where the downstream water is at. The downstream water is a little bit lower in elevation, so it needs to increase in elevation before the jump until it comes to the conjugate of the normal depth downstream. This is complicated stuff, but we'll look at a couple of different ways of understanding it. So here's the rating curve, and this is the thing that you need to reflect on a bit further, but what you should keep in mind is the tailwater curve is more efficient. So it's lower. That means for a certain flow rate, for a certain Q, the depth of the tailwater curve is less than the depth of the jump curve. So since the depth of the tailwater curve is low, that just means that there's going to be gradually varying flow, and then the hydraulic jump will occur. So this is a downstream jump. A downstream jump. The jump is going to be further from the gate if you have a really efficient channel. So like a smooth channel downstream. Or it could be that it's a wide channel, and so that the depth is going to be relatively low. So that combination of characteristics means that if you have shallow depth downstream, an efficient channel, that the jump is further away from the gate. The jump is moving away from the gate. So that's when the tailwater normal depth is less than the conjugate depth of the hydraulic jump. But the other extreme is that the jump moves upstream, and it actually submerges the hydraulic jump, in this case, when the tailwater is not very efficient. When the channel downstream is like a rough concrete or maybe a shallow slope, or it could be that you have a relatively narrow channel. Just for whatever combination of reasons, the Y2 depth is deep. It's deeper than the conjugate of the hydraulic jump. So just based on how much the gate is open, this dashed line represents where the hydraulic jump wants to jump up to, and the downstream depth is greater than that. So you're not going to get the same visual experience with a submerged jump like this. It may just look like a few flutters and ripples on the surface. You're not going to see those vigorous rollers and the turbulence and the entrained air that you do on the other types of hydraulic jumps. So if we look at it from the perspective of the rating curve, this time the tailwater rating curve is above the jump rating curve. So that means for a certain flow rate, the tailwater depth is deeper than the jump. So it drowns the jump. The hydraulic jump is submerged. And it may be that the gate itself is also submerged. So those are the two cases. The jump can run away from the gate, or the jump can come toward the gate. And those are the reasons why. Let's think about momentum depth diagram. This is the momentum depth diagram, and we created an Excel spreadsheet and saw how to set one of these up. And if we have an initial depth of 0.6, by the way, critical depth is the minimum point, right? So this is the critical depth, maybe 0.75. But if the depth is 0.6, go over from 0.6 to here. This is how much momentum it's got. Its conjugate depth is right there. So if the initial depth was 0.6, then it would jump up to a depth of about 1.1, a little less. But if you have a shallower depth, 0.3 for this amount, for this momentum depth diagram, if your initial depth was 0.3, so then we're here, it's going to have a much larger jump. So how far away, the length of this line represents the change in elevation that's experienced during the hydraulic jump. So small change of elevation, big change of elevation if you start off with a shallower depth before the jump. So the Y1 is further from the YC, then that means you have a higher Froude number. It's going to be, for a bigger Froude number, a bigger difference between the Y2 and the Y1. The ratio between them increases as the Froude number gets higher. So our book goes through different jump types and can classify, what kind of flow patterns are seen for the Froude number. So an undular jump is where it's just barely a hydraulic jump at all because the Froude number is so close to 1. A weak jump is also maybe not even visible, but it has typical flow patterns as indicated in the sketch here. An oscillating jump is considered maybe a little bit destructive, and it generally should be avoided if you're designing a hydraulic jump downstream of a spillway, because the flow patterns cause the water to go downward and interact with the bottom of the channel. And so they're considered destructive. But the sweet spot for dissipating a lot of energy but not having flow vectors that are going down towards the channel would be a stable jump, which is the upstream Froude numbers between 4.5 and 9. Last thing I wanted to point out is that there are a couple of different ways to estimate how long a hydraulic jump is. The length of the rollers and the length of the jump itself. The rollers are where you're seeing a little bit of foam and white, like the white entrained air. So you could use a figure where you've got the Froude number on this axis, and then you intersect the curve, and then you go over to the left side, and that gives you a ratio of the jump length to the depth downstream. So the length of the jump relative to the depth. So that means you'd solve for Y2 using the Bellinger momentum equation, but then you'd use the initial Froude number upstream to reflect off the nomograph and find the y-axis. And so if it's 6, then that means that the length of the jump is 6 times longer than the depth of the water. So that's one approach, is this Bureau of Reclamation nomograph. And there's also what's known as the Hager jump equation, and that is also a ratio of jump length, but in this case to the upstream depth as a function of the Froude number upstream. And then there's something our book calls just the another jump equation, where there's just some empirical factor A that's given, and they say that the length of the jump is usually 5 to 7 times the difference in elevations. So that's all the time we have for today. In fact, I've stolen a minute from your life. It's 1:51, so I'll give you back that time with interest next time. Let's just take one final look at the announcements here. So homework 11 is due on Friday. You can get a start on that, and let me know if you've got any questions. Take care, everybody. I'll see you on Wednesday.